So we've learned the principles underlying special relativity. We learned that physical laws are identical in all inertial reference frames, and that one of those physical laws is that the speed of light is constant. Now from those two principles we can derive all of the special relativity that we've learned. And in order to make all our mathematics easy, we introduced the concept of a tensor. And a tensor is the generalization of a vector, or a scalar. It's a geometrical object describing a physical quantity. And because it's a geometrical object and has some real physical meaning, if we change our coordinates, then we have to change the representation of that object in our various basis vectors in a well-defined way. And this is the transformation that all tensors have to follow. And we know that we have all sorts of algebraic processes by which we can turn one tensor into another, which means we can do all the kinds of things we normally do in physics with tensors, just as we often do things in physics with vectors. We also learned about tensor fields. A tensor field is just a tensor for each point in spacetime. We've already had experience of various kinds of tensor fields. Indeed, the electromagnetic field is a classic example. Classical mechanics, that's two vector fields. We're going to see that they can be combined into one tensor field. And we expect that because we can see that in different reference frames, magnetic fields come and go. Now we know that when we don't have forces, that the total energy momentum for vector is conserved. Now when we do have forces, of course we expect the energy momentum vector to change, and we expect it to change. The fall force, if we're going to define one, is going to have to be the derivative of the energy momentum with respect to proper time. Why does it have to be that? Well, it has to be a 4 vector, so the energy momentum 4 vector is the obvious choice. The 3 force is the derivative of the 3 momentum with respect to time, so it has to look something like this. But we couldn't just use a normal time coordinate, we had to use the proper time because we had to make it a scalar. Otherwise this thing wouldn't transform like a 4 vector. It would transform, this bit would transform like a 4 vector, and the time coordinate would transform differently. So this transforms correctly, so that must be what our 4 force is. So now what's it going to be in terms of our electromagnetic field? We know what it has to reduce to. In terms of the 3 force, we know that the force on a charged particle due to the electromagnetic field is just the charge of that particle times the electric field plus the velocity of that particle crossed with the magnetic field. So we know that it's going to have to depend on velocity in some way. And we know we're going to have a 4 vector. I write it as a covector, but we can choose our indices to be up or down as we like. We know it's got to be proportional to the charge. And we know it's got to end up being something to do with the 4 velocity. Now we could just make it proportional to the 4 velocity. So the easiest way to make something one 4 vector related to another 4 vector is just to make them proportional to each other. So I could do something like this and have my electric field be just a number. Now of course we know it's more than just a number, so this is too simple. So we need to make it a bit more complicated than that. So what kind of object can I put here so that I can follow the rules for contracting things and end up with a 4 vector? Well, the absolute simplest I can do is something with 2 indices, like that. So that's the absolute simplest I can do, and that at least has enough structure in it that it can contain something the size of a vector, like an electric field or a magnetic field. So here's our guess, where this thing here is some kind of electromagnetic tensor. We don't know much about it. Alright, let's see if we can figure out some of its properties. Let's have a look at this object here. What's that? That's a scalar because we're summing over this index. By definition it's this. And we know that for a massive particle, the momentum is just the mass times the 4 velocity. And we know that this is, by definition, just the acceleration. The mass doesn't change over time, so this is just... And in our assignments, we calculated that this was 0. So this scalar is the same in all inertial reference frames, and it's also equal to 0. So what are the consequences for our electromagnetic tensor? Let's have a look. Let's contract f with this u. So if we look at that and we force that to be 0, then we know that this part is of course symmetric because we can exchange the order of those two easily. So if I just add 2 of these together, I'll still get 0. Remember, I'm summing over mu and u. I can relabel those to be the other way around. And since I can choose any of these I like, I can choose any choice of 4 velocity that I like, I know that this must be antisymmetric. So this tensor here must get a minus sign every time you swap the indices, which means of course the diagonal terms are 0. So we might have expected that, because if you think about that, that means that in this tensor, if I was to write it out as in matrix form, we have 4 zeros down the diagonal, and we have 1, 2, 3, 4, 5, 6 independent components here, and just the minus of them on the other triangle. So these two triangles have 6 independent components. What's interesting about 6 independent components? Well, that sounds an awfully lot like 2, 3 vectors, doesn't it? Something like an electric field and a magnetic field. And in fact, if we make the following choice, then it turns out that this equation here gives us exactly the Lorentz force law. Let's check that. Now the easy limit to check this is for when our particle is non-relativistic. Anyway, let's look at one of the space-like components. So we've got, say, F1, which would be the x component. Now that's defined as, remember we'll need a minus sign when we're going from the vector to the covector on the space-like components. And we're going to get on the right-hand side, right, so this thing here is just in the limit that we have a non-relativistic particle and in a non-relativistic frame, then this proper time is just the normal time, and this is just the normal force, or the x component of it anyway. And on the other side we have this line, and our fall velocity in the non-relativistic limit again has gamma equals 1, so it's just, and if we expand that out we get, which when we take the minus sign, is just the x component of the normal Lorentz force law. And of course if we do F2 and F3, we'll get the y and z components respectively. Let's have a look at the time-like component. Now remember, the time-like component in the energy momentum tensor is energy on the speed of light. And again, for a non-relativistic particle. And this, of course, means that the work done is going to be equal to just the electric field dotted with the velocity, as you'd expect.